Hi everybody, I'm Letícia Madureira from Brazil. Today I will present to you my solution to the multi-body problem in chemistry using Gaussian orbitals. In computational chemistry, physical properties are calculated by computers instead of obtaining them experimentally. For example, computational chemistry can be applied to medicinal chemistry, material science, and method development in quantum chemistry. All these properties are taken from the wave function of the system you want to study. The first problem we will look at to understand how to obtain properties by operating on wave functions is the hydrogen ionic atom. To calculate the energy of the system, we need to solve the Schrödinger equation. Here we have the Hamiltonian operator acting on the wave function, which is represented by a psi. The Hamiltonian operator is composed by two other operators, the kinetic energy and the potential energy. By substituting the symbols for the expressions of each of the operators, we obtain the analytic expression of the electronic Hamiltonian operator for the hydrogen problem. The first summation contained in the Hamiltonian represents the terms that consider the kinetic energy of a single electron and its attraction to the atomic nucleus, which is of the opposite charge. The second summation is the two-electron term, as it considers interelectronic repulsion. In the single electron case, the repulsion is 0 because there is a single electron, and we are avoiding auto-interaction. Increasing the difficulty of the problem, we will consider the multi-electronic problem. Increasing the difficulty of the problem, we will consider the multi-electronic problem. The multi-electronic system is any system that has more than one electron. To solve it, it is necessary to use some approximations. One of them is that the wave function represents the product of molecular orbitals. Each molecular orbital is the linear combination of the atomic orbitals. The linear combination is weighted by contribution coefficients. Another very important approximation is that the atomic orbitals can be represented by Gaussian functions. This is done because of the Gaussian product theorem, which tells us that the product of two Gaussians is a third Gaussian. The use of these functions in this case has other advantages. The integration methods for this type of function are well known, and computing them requires less computation time as well. But we still want the energy of the system, right? To get it, in this case, we use the Hartree-Fock methodology, which approximates the Schrödinger equation for multi-electron systems. In the main equation of the method, we have the matrix of the Fock operator, analogous to the Hamiltonian. The capital letter C represents the wave function. The letter S represents the superposition of the orbitals in space, that is the overlap, and the epsilon is the energy. To obtain it, you need to implement the algorithm called self-consistent field. In it, you first take the Cartesian coordinates of the molecular system, form the molecular orbitals by using basis functions, and these basis functions are parametric data of atomic orbitals obtained from the basis set exchange. With this, the Fock matrix is formed. Next, it is diagonalized. The algorithm then analyzes the convergence of the values obtained. If convergence is achieved, the energy can finally be calculated. If convergence is not achieved, a new Fock matrix is formed and the steps are repeated. The Fock matrix contains the sum of three elements: the potential energy, the kinetic energy, and the P element. The P element represents the linear combination of interelectronic repulsions, represented by the Coulomb matrix denoted by G. Each of these elements of the Fock matrix is calculated via a Gaussian integral. The first to be calculated is the overlap matrix, which will construct the molecular orbitals. In this case, the operator S represents only the combination integral between the atomic orbitals. Next, we calculate the kinetic energy integral, whose operator is represented as half of the Laplacian operator. Next, we calculate the attraction between the electron and the atomic nucleus, which have opposite charges. This operator is inversely proportional to the distance. This means that the further apart the nucleus and the electron are, the less attraction there is between them. Finally, the repulsion integral is calculated. The operator denoted by G is inversely proportional to the distance. The smaller the distance between the electron, the greater the repulsion. Now, I will show you my application called quantumfoca.jl. The library developed is available on GitHub with an open source license from MIT. The documentation can also be accessed and the library can be imported by REPL. Here is a brief example of how to use it. First, I access the REPL. When I open it, I import Quantum Foca using the command using Quantum Foca. And let's test with a benzene molecule. The XYZ file is already saved. To read this file, I use the molecule method, from where I can get the Cartesian coordinates, the symbols, and atomic numbers for each atom in the molecule. Next, I will build the basis set of atomic orbitals using the build basis method. From this, I can then calculate each of the integrals mentioned: overlap, kinetic, and the attraction. Finally, I would like to thank you for your attention, ask you to give the repository a star on GitHub, and use the package. Any questions, it is just contact me on GitHub, on Slack, or in the comments. Thanks to the event organization for giving me this opportunity.